Welcome to GabVersity, where facts murdered your feelings and got away with it. Hello everyone, Perry, Pilot, Nelly, we've got the whole family, and this is going to be heavy mathematics based. So if you're looking at falling asleep, this is the place to be. I hope all of you are doing very well. Lovely to see you. Interesting. Okay. I may do that. Welcome to Cyanide. Welcome to Nelly Bill. Oh no, my charger is going down. Let us come back. He dedicated it to me. I figured when you said that. But that I will definitely have to watch. So, we cannot... Hey, welcome back to the world. Cyanide and Kuzgan and Dylan and Perry Pilot and Jillian, all these very special and intelligent people. All showing up. Susanito, the whole world is coming back. The key to quantum mechanics. I am great, my dear. Thank you very much for asking. Lovely to see all of you again. Your witty and intelligent self is back. We cannot ask in quantum mechanics where the particle is at a given time. What we can do is ask for the particle's average. Yes, a certain amount is a good way of describing it. Right? An average or mean position as a function of time. And what that means is that at any given time, what would be the average or mean position? For those who know Honest Joe from the Gab Smack channel, my brother's doing a documentary on Honest Joe and it's really good. Alrighty, I'll show it to you when it's ready. Cyanide Hines. Interesting. Alrighty, so to see this we need to recall the probability function. Now we spoke about this last time, if you remember, right? This is true, you could. You absolutely could. And so we're going to use probability densities, and we've spoken about these. If you haven't seen these, you got to go to the last few lectures, and I use the analogy of looking for your phone in the house. What is the probability of finding your phone in a certain location? Some people have long memories here, it seems. Alrighty. So, I'm going to give you a die. Okay? Now here is where the mathematics begins, as does the confusion. Right? If you have a die that you throw and the die has numbers 1 to 6 on it and it's a normal fair die, the probability of each number coming up is 1 in 6. Now the sum of these probabilities is what it looks like in mathematics. I'm going to show it to you right now. Let's get ready. Here she is. We have the sum. This is sigma, which means the sum from n equals 1 to 6. I'm trying to do it through the phone. It's not working very well. All right. That means the sum of n equals 1 is npn. What does that mean? That means the probability of the number showing up. Well, it's n over 6. Right? Which is 21 on 6. Why is it 21? Well, 6 plus 5 is 11, plus 4 is 15, plus 3... Oh, my pen ran out. Let's get another pen. You're rubbish at maths. Oh, Julie, I'm sorry. Well, I'll do my best, but if you get confused, don't worry. It doesn't mean anything except for you just had a bad maths test. That's my rule. 6 plus 5 is 11, plus 4 is 15, plus 3 is 18, plus 2 is 20, plus 1 is 21. There it is. 21. And here, n is 21 over 6, and that equals 3.5. Alright, so all we did was add up. My math teacher was awful, yeah. That's normally what I tell people. I say, if you're bad at maths, it's probably because you had a bad maths teacher. Because maths is not hard. It's just they make it look hard by starting to scribble numbers, and they don't give you analogies, right? So all we did there is figure out what is the average value that would show up. All right. Well, what does that mean? That's how you test if... I'll go along with that. That's how you test if a die is fair, right? So let's say you go to a casino, right? And you think they're cheating you. What you do is you check the numbers that pop up, and when you add up all the numbers and you divide it by 6, you should get a multiple of 3.5. That's all it means. It's that simple. It's like I'll give you even a better example. If you go to the shop and you get a bottle of milk, and instead of charging you whatever the average is, like let's say the average is $2, right? So it might be $2.20, it might be $1.80, but all of a sudden you go to Walmart. Well done, Danny. That's exactly right, my friend. So you go to Walmart, right? Let's say in America, and every time you go to Walmart, the milk is always $3.50. Let's say, right? I'm not picking on Walmart, so I'm just picking a name, right? It's always $3.50, but everywhere else it's between $1.80 and $2.20. Well, then you know that the milk, you're getting cheated at Walmart, and that's all it is. All that whole complicated maths is just that. And the way to do it is you add up all the milk prices everywhere, and you get an average. So if the average is 2, but at Walmart you're always getting $3.50 as the average, then there's clearly something going on, right? Or they have really good milk, or popular milk or something. All right. So here, right, this is what would happen. This is what would happen if you kept organic. It could be if you kept getting an average on the die of 3.86. Discovered angle, side angle was useful with parallax. Oh, there you go. That's awesome. If you get oh, politics. Wherever you go, there's politics. If you get an average on the die at the casino over time, instead of a multiple of 3.5, it's like a multiple of 3.86. Then you go, hey, the casino's ripping me off. And that's actually a good exercise if someone here actually goes to casinos, right, for a living, and you play, I don't know what games they have, whatever has the die, right? What you do is you count them, write all the numbers down, and then divide it by 3.5. If you get a whole number, then you know that it's all good. But if you get a number that's not it's not a whole number, then 3.5 is not the average. There's something going on, something fishy. You know, there might be a weighted die. That's how you can pick it up. So mathematics can show you if the casino is ripping you off, for example, right? So this is how mathematically it looks. You ready? Here's some more maths. This may or may not make sense. Dome Father was shouting out at you. Hey, the Dome Father. I'll say hi back to him. +1 and -1 system, but it's hard to keep up. Real life user, I guess I'm gonna mess around Friday Dome. Hey, the Dome Father. Why wouldn't that take a very long time to get accurate results? Love you. I'm headed for bed. Have a beautiful sleep, Pastora. Always a pleasure to see you. You are absolutely right that the longer you take it, the more accurate you're going to get. You're absolutely right. If you took only like 5 throws, then you're sort of kidding yourself. But you'd have to be there for an hour or 2. But even within the hour or 2, you could still have some problems. Yeah. So then you'd want to measure multiple tables. Hey, no Tifa. She's cooking. No Tifa. All right, here we go. So this would be, let's say that they wanted to rig the system, right? So what would happen is, here is the mathematical equation. 1/7, right, of the sum from n equals 1 to 5, n plus 2/7 by 6. And that equals 27/7, which is 3.86. So if anyone doesn't get the maths, don't worry, right? Because I'm for those who do get the maths, awesome. If you don't get it, don't worry, that's fine. I'm gonna do it both ways, right? So do it both ways. That was not a joke. All right. Now let's have a look here. Now I'm going to translate what I just told you, but I'm going to translate it into waves. And the difference with waves is that it's continuous. It's not like a die which has discrete components. Oh, it was. In this case, the probability of the function continuous, so instead of a discrete sum, we use an integral to calculate it means. Okay, so now we're going to use integral calculus, right? All right, let's do it. So that's one page that is done. Okay, so all we're doing is converting the mathematics from a sum into an integral. The difference between a sum and the integral, are you going to do it both ways? Possibility of closed timeline curves. Mathematically, possibly, but so far that hasn't been confirmed. You can be in two places at the same time. Yeah, this is the illusion at the moment. Yeah, it could be that way. No one knows if that's happening. If you there's a good if you go to YouTube and look up PBS physics, there's an Aussie guy actually, and he talks exactly about what you just spoke about, and he released it a few hours ago. So that one's a pretty good one if you want to see that. Never seen Rathmitten in pen before these scopes. So I don't know if that's good or bad. All right, we're now going to swap the sigma from a sigma to an interval. Now the sigma was the sum, so the sum of 1 plus 2 plus 3 plus 4. Well, this pen is erasable, so I'm cheating. All right, the integral, right? Instead of adding up 1 plus 2 plus 3 plus 4, we're adding up an infinite amount of numbers. So we're adding up 1 plus 1.1 plus 1.11 plus 1.1111 plus 1.111. We're adding them all up, right? And you can't do that with normal addition because there is an infinite amount of numbers between 1 and 2. So if anyone didn't know that, you now know. There are an infinite amount of numbers, area under the curve, between 1 and 2. Right? That's what Newton realized. He realized, holy crap, if I add up all the numbers between 1 and 2, I'll never get there. Yeah, it's infinity. And between each number, there's an infinite amount of numbers. And between each of those infinite numbers, there's an infinite amount of numbers. So there's an infinite amount of infinite numbers. In other words, it's uncountable. So the amount of real numbers that exist is uncountable. It is not even infinity. It's an infinite infinities. Yeah. All right. So Newton, to fix that problem, designed something, and so did the other guy on the other side of the world. What was his name? Robert Hooke? Not Robert Hooke. You know who I'm talking about. The other guy who doesn't get recognition, even though he came up with it too. Yeah. So they came up with this idea called integration, where they said, if I can get the smallest number possible, that's smaller than the smallest number possible, macro and micro. Well, they're both correct, but you need to know the maths to be able to actually understand it at a deep level, yeah. But to get, I'm still teaching it using examples. How are the quantum twins paired? No one knows yet. There you go. The reason I did my physics degree was to try and understand like what's at the edge of the universe. And then when I finally finished the degree, they don't know what's at the edge of the universe. It's ridiculous. So let's see who we got here. All right, can't even tell anymore. Alrighty, so I'm going to show you the integral. Right. This is how you add up an infinite amount of numbers. Until you made your point. Thank you. That's a good idea, Joker. All right, so what we want is the average, right? Instead of before. All right, before what we were doing was we were saying the average was using sigma, which is a sum of 1 plus 2 plus 3 plus 4 plus 5. Here, what we're doing is we're doing the same thing, but it's with infinite numbers. So we're going the sum of 1 all the way to 5, but every single number in between. Show me the edge, I'm ready. The edge of the universe is in 4 dimensions, so it's where time ends. It's not a physical barrier in the single electron theory. I'm not a believer in things. I prefer to always have a bit of doubt. X, p of xt dx, all right? So this is just the integral version. If you don't get that, don't worry. If you've done calculus, good. Let's move on. All right? Okay, where the limits on the integral cover all values of x where the probability density is non-zero. All right? And all that means, so when I came back to told you about the phone in the room, right? We are looking for the phone in your house. So what we're doing is we're saying that every single location in your house, we're going to add every single infinite location up and then divide it to get the average location of your phone. Because your phone might be in the kitchen more often or something like that. Okay. Now, what we do in quantum mechanics, the probability of function is assumed to be the square modulus of the wave function. All right. What that means, do you think the single electron theory is possible? Let's just say it's not impossible. That's the best I can say at this point. but it is definitely, there is a very good YouTube link to it. If you type in, well, you probably already know, but if anyone else types in single electron theory, type it in Google videos and you'll get some pretty good lectures on that if you have the time. They go for about a couple of hours. All right, the wave function, as we spoke about in the last scopes on quantum mechanics, is the equation that describes the wave shape, which is basically all possible locations of the electron on that wave. Right? It's going to exist on that wave somewhere. Oh, my pleasure. Always a pleasure to have you. Alrighty, so here we go. Anyone who shows any sort of interest comes up upper level into the entry VIP scopes. All right, so here is the equation of the wave function. Okay, the wave function is this thing. Okay, that just means psi is the wave, xt, that means x, which is one physical direction, and t is time. And what we're doing is taking the modulus and squaring it. So that's the modulus, which is the positive absolute value of the wave, and then squaring it. Okay, now how do you do that? Because with a number, here's the modulus of a number. This is 5. If I take the modulus of 5 equals 5. If I take the modulus of negative 5, that equals 5. Right? If I take the modulus and square it, that equals 5 exactly times 5, which equals 25. So with numbers it's easy, but how do you do it with a wave? What the hell? How does that work? Well, what you do is, there it is. It's phi by xt, phi xt. Okay, we call that absolute value. Yes, that is correct. Once you get into complex analysis, they change the name to modulus. The reason being is that absolute value is a subset of moduli. So a modulus with a real number, you call it the absolute value. But once you bring in complex analysis and waves and Hilbert spaces, etc., if anyone who's done that level of maths, absolute value doesn't make much sense anymore. So it's called a modulus, which is the group of everything, including absolute values. All right, so moving on. But good, I love your questions. That's one of the great things about doing it on Periscope, actually. Why is that? Okay. Please focus. Focus, 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 focus now, biatch. No? Even with the magnifying glass, it's not focusing anymore. That's really annoying. Alright, I'm just going to have to draw it. So, x, let's see if this comes out. There we go. When I draw, it comes into focus. Alright, x, so it's x multiplied by p of xt dx. Alright, if anyone doesn't get the maths, don't worry, it's focused. Awesome. If you don't get the maths, don't worry about it. But for those who do, here you go, which is x by the modulus of psi x of t squared dx. And basically all we're saying is that psi x of t, the modulus of that squared, is the probability density, right? As the focal point is skewed. Yeah. Okay, I'll try that. All right, so this here is the probability density. That means that this thing here will give us the likelihood of finding the particle x at a given time t along the wave function. And to get the probability density, we have to get the wave function, get its modulus, and then square it. So that's the steps that we've done. So what we're saying is, if we want the average value of x, right, we've got to get x multiplied by the probability density of x, and we have to integrate that over the all possible locations of x, right? That's all we're doing, right? And then how to do that is by getting the wave function, which is the equation that describes the all possible locations of the wave, and then getting its modulus, which is similar to what I just showed you, the absolute value, and then squaring it, right? And by doing that, you then get the probability density function, and then you multiply that by x, as we said, and then you integrate it across all possible locations. So for those who are not into the maths, right, what that means is that we get the algorithm which shows every possible location that your phone could be in your house, and then what we do is all those possible locations have a certain distance. We get the average distance in a way, and then we square that distance, and that will tell you the possibility over you as a mathematician. Cool. All right. Yeah. Thank you. And then once we square that, we get this magic number which tells us basically what is the likelihood of your phone being in each position in the house. So for example, the likelihood that it's in your bedroom is 20% at any given time. The likelihood at any given time it's in your bathroom is like 5%, you know? And then so you say to yourself, well, if I'm going to look for my phone, the first place I'm going to look for it is the place that it is probably going to be. And let's say that, you know, most of the time it's on your favorite place in the shelf, which I spoke about last time. Then if you do that, hey, Honest Joe's back. All right, if you do it that way, anyway, you know what I mean. So let's keep going. Once again, what is the velocity of your phone? That sounds a bit weird, right? How fast does your phone travel? Well, what we can... Love learning about math. Awesome. Welcome, little one. Lovely to see you. Finding the velocity of a quantum particle sort of makes no sense if you think that the particle is traveling. But if you think of it as I told Ernie Banks in the last episode, if you have a traffic light and you see the light is green, then it goes orange, then it goes red. It's not really traveling, but it looks like it to us as humans because we put it together. That going from there to red, you could call that the velocity of the particle, right? And that's how we think of quantum particles, because quantum particles are really just pixels. You're like a fresh breeze in this shithole called Periscope. I'm sure Periscope will love hearing that one. Oh man. All right. So, as I said, what we have to do now is to get the velocity, we want the derivative of the actual location of the particle. Now, if you remember, and I'm going to draw this for you, remember before I said if x represents your distance, then dx dt is going to represent your speed, right? And I did that. If you haven't seen the last episode, you got to go back and see it so you know what I'm talking about, right? But basically, let's say that x is your speed, is your distance. So let's just say x is, I don't know, whatever in meters, right? Thank you. Then your speed is going to be dx dt is something, you know, meters per second or miles per hour or whatever, right? So that's just the mathematical notation for that. And in quantum particles, as we said, you can't just do something per hour. That makes no sense because you don't even know what the particle is half the time, right? So you've got to say, all right, I'm going to get the average particle's location, and then in another point in time, I'm going to get its average location. And then I'm going to get this weird thing called an average velocity. So it's like I said with the traffic light, you know that the traffic light goes from green to red in like 30 seconds. So that's sort of what we're doing, right? And that's in one direction. Wait till we do multi-direction. All right, so this is what it looks like. Okay. dx dt equals, this here is going to be what x is, right? All right. So d of x dt, in other words, this over time, right? And we have the integral from the one possible location to the other end of x multiplied by that wave, which I told you about. That's the wave function. We take its absolute value or its modulus squared dx. And I'm a hopeless dyslexic. All right, Maggie. Well, lovely to hear that. I'll keep going. All right. And that is basically x by d dt of this. So this is just mathematics. All we've done is we've put that inside. All right, and it's a partial. It's called a partial. I won't explain that. If you know what a partial derivative is, then that's a partial because it's in one direction. All right, so that just equals that. All I did was sneak that inside here, and then all I did was change this because that's squared into this. That times itself, which is the same thing. Which is the same as going by that times that plus that by that dx. So we've just rearranged it mathematically, right? That's all we've done. Now you don't have to know that, right? If you're not good at maths, but for those who are, that's all we're doing. It's called integral calculus or integral by parts. You should do it in second year uni. All right. So we change it to partial derivative inside the integral of the wave function is a function of two variables and what I do the derivative with respect to time. Yeah, okay. So as I said, it's a partial derivative. You don't have to worry about that. But for those who do mathematics, it's... Hey, Dad. Note that we can't apply integration by parts directly to 13 since the derivative inside to expand with respect to time, integration with respect to distance. All right. So for those who are mathematically inclined, right, the partial derivative inside is with respect to time, and the one outside is with respect to distance. So we have to make them the same before we can go the next step. Right? If you're not into the maths part, don't worry. Right? We're still on the traffic light idea at the moment. All right. So we know, right, by using the Schrodinger equation, right? The Schrodinger dyslexics are actually great at math, easier to do algebra. I'm not really surprised. Hey, Boss Briggs. Okay, now remember, every equation in quantum mechanics is like gonna probably have this h, because if you remember, I told you h is the pixel of the size of this universe. The smallest pixel in this universe is the width of this thing, right? So that squared over 2m, right? And that's h bar, and then we've got the second derivative with respect to x. Now remember, as I said, the first derivative. Yeah, I did. Thanks, Dad. The first derivative is like if you had distance, then the first derivative is speed. The second derivative would be acceleration. Okay? So distance, when you derive it, you get speed. When you derive that, you get acceleration. Hey, Chucky. All right. So that equals the complex number I, which is the square root of -1, multiplied by h and d phi dt, which is this average velocity idea of the wave. All right, and all we have to do is, sorry, we're going to do a bit of maths here. We're just doing some rearranging. So all we do is put IH on the other side, put it over here, and you get this. And then you get d phi dt equals h bar over 2 times the mass of the electron or the particle, whatever it is. And then we got the partial derivative, the second one with respect to x, of the wave function, okay, minus 1 over I, which is square root of -1 by h bar, which is Planck's constant, as we said, the width of the pixel divided by 2 pi, and then v, which is the potential of the wave function multiplied by psi star, which is the conjugate. Okay, now the conjugate, I have to explain what that is very quickly. If you've done complex numbers, you know what a conjugate is. But a conjugate is like the mirror image of numbers, right? There is an alternate world that humans have discovered through complex numbers. And that alternate world is a mirror image of this world. And we can't see it, but it copies us in reverse. And Hawking's reckon that's related to parallel universes. So we can't see it, but it appears in mathematics all the time. And what happens is that the alternate world and our world split, and then when they come together, it pops up as real. So the number 5, for example, right? I have 5 bananas, right? I can't have, you could have 5.1 bananas, but you can't have 5 plus the square root of -1 bananas. That makes no sense, because there's no real number that we know of that when you square it, when you times it by itself, you get -1. Right? But 5 plus the square root of -1 has a mirror image number, and that is 5 minus the square root of -1. And they exist in alternate universes that copy each other in reverse. And we use them in quantum mechanics because somehow they split, and then when they come together, it pops up as something real. Oh, awesome. Thank you. So no one knows how this happens, but mathematically we see it all the time. And Hawking's reckons it's alternate timelines. And these timelines sort of diverge, and then when they pop back together, they pop up in our universe. No one knows if that's true or not. I mean, but you could imagine it like that at the moment, right? All right, so now the term simplifies, and we get this equation. This is the equation if you want the average velocity. So we're coming all the way back to what I said about the traffic lights. We're trying to figure out the speed that it looks like this particle is moving, right? So we get the traffic light, we see how long it goes to go red. The mathematics of doing that is this. Why, thank you, Boss Briggs. Boss Briggs! All right, so this is the equation. If you want to know the velocity, all you have to do is get h bar, which you'll know, 2 times the mass of the electron multiplied by the square root of -1, all times by x, which is the distance. And then on the inside of that, so that is multiplied by this thing here, which is the conjugate, as I said, the mirror image, derivative with respect to x, okay, multiplied by the wave function, minus the wave function conjugate by the partial derivative of psi, which is the wave function with respect to x. Okay, you don't have to get this, by the way, I'm not expecting you to get this. Minus h bar over 2 times the mass times I again, multiplied by the integral of that, which is the same as this, right? But now it's the integral of that, dx. Okay, so that equation looks really long, but it's actually not that difficult because a lot of those terms are repeated. And all you have to do, all it's saying to you is that if you know the mass of the particle, if you know the average location of the particle, then you can find out the average velocity of the particle. That's it. That's all that work. That's all it's saying, right? So you want to know where these particles are going to go and where over time, then that's the equation you use. Okay. Now, here is one assumption so that this works. None of this works unless the electron exists, right? So when I said to you guys before, you're looking for your phone, there's no point in looking for your phone in your house if there's a chance that it's not in your house, right? If your phone is at my house, then you're wasting your time looking at your house. Bingo. That's right. So you basically have to make an assumption that if you're going to do this equation, that you know all possible locations of the particle, right? In other words, it has to exist. It can't just be some imaginary wave. Hey, the Dome Father, he's back. Okay, that's all it is. So we are confining the location of this phone to a certain place. We're going to say, I'm going to look in Boss Briggs's house and Dome Father's house. They're the only 2 places it could be. I'm not going to go look at, I lost my lecture notes. No. Excuse me, I lost my lecture notes. I'll be back. I'll be back. I'll be back. Bloody hell. Alright, are we back? We're back. Sorry, we got them back. Alrighty, now I have to make sure I cover them. GabVersity, where the wind doesn't care about your feelings. You stole the phone, to be honest. Well, that could happen. This is true. Alright. Outside the region in which we have confined it. Okay. Black hole. There's no such thing as particles inside a black hole. In a black hole, space becomes time and time becomes space. But I won't talk about that in this lecture. We will be doing that in our astrophysics lectures, which are coming up soon. Okay. So, now what we want is... Okay, here we go. So here is the final equation. If we assume that we know all possible locations of the particle, then a lot of that mathematics is going to end up simplifying. Thought your lecture papers went there. I am on YouTube. If you go to GabSmacked, GabSmacked, just like Ernie did, he just gab-smacked me with the black hole. You need to keep these lectures. Yeah, absolutely. I believe the Dome Father is going to be setting it up so that in the future you'll be paying for most of them, and for some of them you'll get them, or you can become a member. I don't know how it works. I think the Dome Father is doing all that. All right, so have a look at this. Here is the final equation if you know where the particle is. See, it's a cheat. If you know where the particle is, then dx dt, all right, which is this velocity, it's so simple now. Look, h over mi, which is the mass by the square root of -1, times the integral of the wave function multiplied by the derivative of the wave function with respect to x. All right, that's All it is, that simple. All that mathematics comes down to that final equation. So this is the one you want to know. In quantum mechanics, the equation you want to know, right? Where am I? It should be h bar. I don't know why it says h. I think that's a misspelling, but it should be h bar. H bar over the mass times the square root of -1, multiplied by the integral, which is the infinite sum. Remember, integral is like an infinite sum. That's why you call it area, right? Of the wave function multiplied by the derivative of the wave function with respect to x, right? And that's a partial derivative. Right? Because did you moderate me? By the way, remember that the wave function is, at the moment, it's two-dimensional, right? The wave function now is two-dimensional. It's a two-dimensional wave. So that might be weird to put in your head. When I was telling you before about the skipping rope, right? It's actually a skipping rope that goes like that and like that at the same time, right? But it's actually in 4 dimensions, because you have 3 spatial dimensions and a time dimension, and that makes it 4. And what happens is, it's a wave that when you go like that, it's going like that and like that and like that, and in 4 dimensions. So it's actually a snake as well, right? Very hard to imagine. There is a guy that's really good at explaining it. If I find the YouTube link, I'll tweet it at GabVersity. All right. So the next formula is momentum. We want to find the momentum of the particle. Does anyone here know what momentum is? Momentum. I'm going to give you a question. If a fly is traveling at 10 kilometers an hour and a truck is traveling at 10 kilometers an hour, both at the same speed, which one has more momentum? Which one has momentum? Momentum, fool. Which one has momentum? The transfer of energy? Not too bad. Not too bad. It could be expressed in that form. The fundamental mathematical interpretation of momentum. Right? So which one has more momentum? The truck or the fly? And they're both going at the same speed. The train. That's right, the train would have more than splat. You know, I ask these questions to get these answers. They're so funny. I love them. Exactly. And why does it have more momentum? What is the difference that makes it more momentous? What is it? Based upon mass. Bingo. More mass, mass. It's heavier, mass. Bingo. Everyone's on the money. All right. So we want the momentum of this quantum particle, which once again sort of doesn't make sense, because like we said, when I said to Chucky yesterday, right? The traffic light. The traffic light is where we're trying to fit. What's the momentum of the traffic light as it's going from green to red? It sort of makes no sense, right? But what you do is you get the mass of that light, right? Of that particular traffic light, which is the mass of the quantum particle. And then you figure out over time where it's likely going to be. So you get the likely momentum or average momentum or momentum density. You can get these type of things. So here is the equation. It's just mass times the average velocity. That's it. And we said that the average velocity was h over mi integral, right? Phi multiplied by d phi dx dx. I just showed you that, right? So all you have to do is times that by mass. But hold on, look at this. Look at this. Velocity has mass in it. So if I times this by mass, m times 1 over m, that's going to cancel out. So momentum is this. Basically, it's just a simpler version of that is now this. It's h over I, h bar over I instead of h bar over mi. Me, right? H bar over I, integral phi d phi dx dx. There it is. That's it. There is your mathematical equation for finding the average momentum of a quantum particle. Problem solved. It's not actually that hard in mathematics. Okay. Okay, let's go. So, using some mathematics, which I won't show you right now, you can actually express this equation using different fundamental variables. Now, why is that important? I'll tell you why it's important. Let's say that, let me pick one person here I haven't picked before, with a vision. So we've got someone here called with a vision. All right, I'm going to say to you, with a vision is a white male who's 20 years old, right? Hey. So that's one way to describe with a vision. Let's say, I'm just making it up. I could be completely wrong, right? Right. Now, let's say I want to pick another way to describe with a vision. I could say with a vision is a human with male genitalia and speaks English. All right. So he's a human with male genitalia who speaks English, or I could say he's a white male age 20. Now, they're two different ways to describe with a vision, but they're both true. Now, why is that important? It's important because if you're trying to describe him to someone else, if you're missing some of the details, you can give them the other details. Or if you're missing the other half, you can give the first half, right? And that's how you discover who it is that you're talking to. So the more you have, the better. So obviously, it's the same with describing quantum particles and their motions. You want to have those equations using different elements that make them up. So then, if you have some, you can find out the rest. It's just a process of elimination. The more details you have, the better, right? So here is another version of writing it. Instead of calling it this, which is mass by average velocity, you could call it h over I by the integral of psi, the conjugate of the wave function, by d psi dx. Psi is the wave function. I'm going to say psi from now on. Psi is wave function is psi. D psi dx dx. Right? Here's another version. Right? H bar delta dx, which is just an operator over I. Okay? That's another way. If you don't understand that, don't worry. That's called an operator. If you've done advanced calculus, you'll know what that means. Okay? And then the other version is this, average momentum, right? Because that's probability density. Sorry, I stuffed that up. That's probability density, right? Which we spoke about ages ago. And then what we do is we put the probability density in here, which is, we have the integral of psi conjugate multiplied by probability density, right? Which is that multiplied by this, right? So that means that we want the partial derivative of this with respect to dx. That's it. So that just goes into here. That's all. Okay. It's just substitution, basic algebra mixed with calculus. If you've done that, awesome. If you haven't got that, don't worry about it. You're still going to follow. Okay. 6 out of 10. Next. Okay. Here we go. This is the recipe for finding the average values of any quantity in quantum mechanics. There you go. So anything you want in quantum mechanics, you can use that basic mathematics if you know calculus and algebra, and you'll be able to find any average values, which is pretty awesome. All right, so express the quantity you're interested in terms of position and momentum. Okay. There are other quantities such as spin, but they have their own special treatment. We'll get to that later. Hey, my dog Sherlock. And then sandwich this expression between psi conjugate and psi as we've done with momentum, and then integrate. All right, so that's it. What we just did is the end. Done. All right, so that is the basic mathematics. And where's the next page? 7 out of 10, 8 out of 10, 9 out of 10. Ernie Banks. Okay. All right, next one. Okay, here we go. Schrodinger equations. I'm going to show you the Schrodinger equation. The Schrodinger equation is the simple mathematical equation invented by Schrodinger, which roughly shows at slow speeds the movement of a quantum particle, right? The wave is where the particle can exist. So imagine a skipping rope. The particle can exist along whatever shape that skipping rope is making. So maybe you're doing it like really, really fast, right? That's not a dirty joke. Then if you're going fast, it's going to be like little waves, right? The particle could be along there. That might be like a high energy particle or something. You're just making it up. All right. And then we'll stop after this, I think. All right. Here is the equation. The equation, negative h bar squared over 2m, second derivative of the wave function with respect to x, plus the potential of x multiplied by the wave function equals e by the wave function. That is the Schrodinger equation. In other words, if you have the potential and you have the wave function, right, you can find out what the energy is. Or if you have the energy and the potential, you can find out what the wave function is, as long as you have the location being x. Okay, that's it. That's all it is. Problem solved. Okay. The spatial part 1 of the Schrodinger equation. Found the cat. Excellent. Excellent news. The cat has been found. Alright, so here is the equation for spatial ability. Spatial ability. The spatial part of the Schrodinger equation. So remember, the Schrodinger equation is 4-dimensional. Right? We're only doing at the moment, he's dead and alive. Correct. The Schrodinger equation is, at the moment, we're going to keep it as 2-dimensional. In other words, 1 dimension of space and 1 of time. And that makes it 2-dimensional. And then the subset of that is the space. So you have where the location, all the possible locations of the particle in space for every given time, right? So over time, the particle could be here, but in one, just the space of the particle, without time itself, all possible locations. And that is this equation, right? Second derivative of the psi with respect to x equals 2 times the mass over h bar squared, and then in brackets v minus e psi, which is the wave function. So that is just the simplified version if you're looking just for space, and that's called the time independent. So we're not focusing on time at all. It's just a lower grade version of the equation, right? Okay, let's move on to the next bit, and then we can, I think that'll be it, that'll end it. Okay, yeah, that'll end it. I'll give you the equations and then we're done. Okay, so here is the time component. T is e to the minus energy times t over h. So basically what this tells you is the time component of the equation. If you have the energy, you can find the time. If you have the time, you can find the energy. And it depends on the wave function, so that's charting it out. Okay? The value of the energy completely, this is the multi-dimensional version. Okay? Psi of xt. Psi of xt, that means the wave function with 1 dimension of space and 1 dimension of time. Right? And that is psi of x, right, times e to the minus, should be an I there, I, e t, so square root of negative 1, that's the energy, that's time over h bar, which is a constant. And as I told you, h bar is the rotating version of the pixel. So the pixels that we have in the universe, we're all made up of pixels, right? That's the size of the smallest possible pixel in this universe is the number h. Alright, that ends our quantum mechanics for today. I've got another couple of hours of quantum mechanics, but I will probably do them on my own. If anyone is interested, tetrahedron pixel. Hey, hey, hey. Okay, that's about it. Oh, I am honored. You guys are great too. Your questions make it hilarious. Little pyramids. Alright, thank you, Boss Briggs. I wish all my professors were autistic and may have received a doctorate. That's funny. Alright, I'm going to go do some more mathematics on my own. Absolute pleasure to see everyone, as always. And don't forget, GabVersity, where facts murdered your feelings and got away with it.